we do have our test coming out Wednesday. And you, at this point, have the opportunity, if you wish, you may make your own formula sheet for this. Now, this means formulas only, not examples, not worked out problems, formulas. Like you could give this formula and then write the rule of E is between 0 and 1, E is greater than 1, E equals 1, that type of thing. But you couldn't write out through this whole problem that shows out those things. You could write out like this part right here. So if you choose to do it, you will need to make sure that you attach your formula sheet with your test when you turn it in. You can also choose to memorize all of any formulas needed. So we are looking at 9.5 DeMoivre's theorem. The DeMoivre's theorem. Now, the first part of this section is very easy. Graphing complex numbers. Now, anytime you're graphing complex numbers, one of the key things, and I'm sure at least one person in here is going to forget to do this. To draw your graph, it's going to be the same standard rectangular coordinate. Label, real and imaginary. Put your labels on there. Yes. Because if you put, for example, if you were graphing to point 2, 3, you couldn't graph that on this coordinate plane. Because 2, 3 has 2 real numbers. Whereas labeling, so when we're graphing an imaginary number, anybody remember doing this before? Okay? So let's just do if I say 3 plus 2i. What is the real part of it? 3, what's the imaginary part? 2. So 3 plus 2i would be the points right there. 3 in the real direction, 2 in the imaginary direction. So if I had negative, so what about -1? Yeah, how is this the point? -1. Where would -1 be on this? Okay, from here, where do I go? Left 1, right there. So this is just like a number line here. So if you have a number that doesn't have any imaginary components, it will be somewhere on the real axis because it is just a real number. So if you have 2 minus I, you go 2 in the real direction, -1 in the imaginary direction. Now, unfortunately, this is by far the easiest part of this homework. It's actually one of the more challenging sections. So, standard notation, we're going to say Z equals A plus BI, where A and B are real. In other words, we've got 2 real numbers, and then I means B times I is imaginary. This is just like what we were doing up here, 2 minus I or 3 plus 2I. When we say the absolute value of an imaginary number, okay, so think back to maybe your pre-algebra days, how did you define absolute value? Okay, distance from 0, which is a good definition. And we're going to use that definition again here with imaginary numbers or complex numbers, where our distance from 0, because this point is 0, right? If we were graphing the point 0, it would be right there. So how far is this point from 0? Well, when you look at it, we could treat it just like this. Which part of this is A? 3. So this is our A. We've got our B right there. So what do you think you can do? Pythagorean theorem, where this is our C, which is how far it is from 0. D. I'm just going to actually split C, but we're going to say A squared plus B squared equals C squared. So the absolute value of Z is going to equal the square root of A squared plus B squared. So what is the absolute value of -3, actually let's go, negative 13 plus I? Okay, first, what is A? -13, what is B? 1. So -13 squared, 169, plus 1, 170. So square root of 170. And let's see, 170 is 10 times 17, so I'm not going to simplify. Now we do have another notation of writing this. So this, yes. So we can say A equals A plus BI. However, we can also write this trigonometrically. When you start looking at this, think about cosine and sine. Where would they be in this? Okay, sine and A. So close, very close. Remember, this would be our R, right? The sine is B over R, which means that B is equal to R sine theta. There we follow that? That's what we've been doing this last while. So what we can do is what would A be? R cosine theta. So we're going to have R cosine theta plus R sine theta times I. And normally, the notation we use, we factor out that R, but it's R times cosine theta plus I sine theta. And that's another way of writing it. Yeah.
So the I is just multiplied by
Yeah. So it's not theta times I, if I put the times here, so I differentiate it. So the I is within the parentheses for the theta. So to write it trigonometrically, what information do we need? Okay? So to write this, say this 3-2 trigonometrically, we need R and what? What? Okay. So how would we get theta? Okay, we'll have to use inverse tangent. So yes. So if we have, let's say, 3 plus 2i, let's write it in trig form. First, what is R going to be? That R is the easy part. Okay, square root of A squared plus B squared. So 3 squared, 9, plus 2 squared, so it's 9 plus 4, 13. So we're going to have the square root of 13 times then how do we get that angle? Okay, inverse tangent of 2 over 3. So somebody do that in your calculator. Use radian, make sure you're in radian mode. So what is the angle? So 0.59 plus I sine of 0.59. So anybody else do that 16 number? Okay. Doing inverse tangent of 2 over 3. So what we're doing is saying tangent of theta equals 2/3 and do the inverse tangent. Anybody else get the same number? I just want to get a second, make sure everybody. Okay, good. So now we've written that in trig form. Now we get to some of the more complex stuff. Remember, z equals a plus bi. So I'm going to say if we have 2 of these, then I'm going to say z1 equals a1 plus b1i, z2 equals a2 plus b2i. And if we're multiplying them, so z1 times z2. Now, algebraically, fairly simple to do this. Boil the two numbers together, simplify. If we're doing it in trig form, what we're going to get is r1 times r2 cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. This is the same if we have it in the form r1 cosine theta 1 plus I sine of theta 1. Okay, so everybody see the connection? Can you read it? R1 times R2, and then parentheses cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So what do you think division, so z1 divided by z2 is going to be? If you have a guess from looking at the multiplication. Okay, subtracting the angles, so what's R1 and R2? Okay, R1 divided by R2, and cosine of theta 1 minus theta 2. Now, exponent. It's a bit trickier even. So we're going to do, if we have z to the n, remember z is r or a plus bi or the trigonometric equivalent. Anybody have a guess from looking at this structure? And without looking at your book. Yes? What? Okay, so that's the general idea, but what's the formula going to look like when we simplify it a little bit? Like we're going to have r, what do you think is going to happen to the r? Okay, r to the n. Cosine of theta times n plus I sine of theta times n. So, if you notice, theta n here, if you look up here further, we had multiplication outside, changes to addition inside. So exponents outside, change to multiplication inside. Does that sound similar to something you've done before? Remember logarithm? We had something similar to that. Okay, the next one. Next one is the complicated one. So, all this, everybody has a general idea, fairly simple, right? Basically just recognize the pieces, plug them in. We're going to do some examples of them. This next one is going to be the more challenging. This is the piece root of z. So if we're taking the square root, cube root, fourth root, the piece root of z. Anybody have a guess what's going to happen with the r here? Okay? Well, you know up here, when you multiply them, you multiply the r. You divide the r. When you raise it to the power, r to the power. Yes. We're going to do this piece root of r. Then, you're going to have inside the cosine of theta plus 2n pi over p plus I sine of theta plus 2n pi over p. Why do you think there's this 2 pi in here? You see the 2 pi here? Why do you think you have that 2 pi? Maybe have a guess. So if you were just looking at this part right here, theta plus 2 pi n, what is this going to do? So you don't have to put this in your notebook, but this is this pi 6. We're going to do theta plus 2 pi n. What's going to happen if I add 2 pi n to this, where n is some number? If I add 0, or if n is 0, what's going to happen to this? Say the same. If n is 1, what's going to happen? Okay, we're going to go around the circle one time. Remember, 2 pi is all the way around. If n is 2, what would we do? Twice around. 3 times. So we are ending up at the same spot every time. Right? Okay. So that's why if you look back here, it's going up to plus 2 pi n. It is going around. Now, if I just said the square root of, or piece root, or fourth root of something, what's the complication in here? So what do you see over here that's not over here? What? What variable is over here that's not over here? N, yes. So n is a complication. So we're going to have to put a rule for what we do with n. N equals 0, 1, 2, all the way up until we get to p minus 1. Because remember, if we're looking at a square root of something, until we get to p minus 1.
Whatever p is.
So, for example, if this p was 5, we plug in 0, 1, 2, 3, 4. 5 minus 1 is 4. Now, why do we do that? Think about this. If we had x squared equals 4, how many answers are there? You could have 2 or negative 2. So there are multiple roots or multiple answers to that equation. So this is what we're dealing with here, is we might have, and we do have, multiple answers to this equation. And we have to find all of them. So if we do square root of 3 plus 5i, actually let's do not square root, just see, what number of roots? Okay, cube root. So when we look at this, back at the formula here, how many of these, what are we going to be plugging in for n? We're going to plug in 0, 1, and 2. So we're going to do all 3 of them. So what's the first thing we have to do with this? Find what? I'll find r and find theta. What is r? Okay, square root of 34. What is theta? Okay, 1.03. Okay, and you did that by doing inverse tangent of 5 thirds. Okay, so 1.03. Okay, everybody with me so far what we've done? Anybody not with me or confused from how we got these numbers? Okay, so now we're going to figure out what are the roots, or the cubed roots of 3 plus 5i. So first, our first answer, I'm just going to call it A1, equals. So we're going to do, plug into the formula, p root of r. So the third root of the square root of 34. The third root, actually to make it simpler, how do you write third root as an exponent? Yeah, raising to the 1/3. So I can actually say square root of 34, and no, this is 34 to the 1/2, right? And we're raising it to 1/3, so what are we going to end up with? 34 to the 1/2 to the 1/3. What are we going to get? 1/6. So this is going to be 34 to the 1/6. That's doing the square root or cube root of the square root. Then we're going to have cosine of, so the first one, cosine of what theta is 1.03 plus 0 over p, which is 3, plus I sine of okay, because remember we're starting at n equals 0. So for our first one we put in 0 here, we're going to get 2 times 5 times 0. Okay, any questions? Okay, now we're going to plug that into your calculator. So put cosine of 1.03 divided by 3, and then times 34 to the 1/6. So what do you get for the real part of it? Make sure you are in radian mode. 1.69. Okay. And what do you get for the imaginary part? So plug in sine of 1.03 divided by 3 times 34 to the 1/6. Actually, you know, 1.69 plus 0.61i. But you guys are getting? Yes. So what we did is just take 34 to the 1/6 and times each one of these parts. Now that's only the first answer. Remember, we have to plug in n 0, n equals 0, n equals 1, n equals 2. So a2 will equal 34 to the 1/6 cosine of, note, theta does not change, but this is going to, now we're plugging in 1, so it's going to be 2 pi over 3 plus I sine of 0.03 plus 2 pi over 3. Hey, does that make sense what we did there? What we changed. And our third one, once we get to it, is going to be a3 equals 34 to the 1/6 cosine of 0.03 plus 4 pi over 3. You see where it came from? So here we plug in n equals 1, here we plug n equals 2. Remember, it is 2 pi n, right there. And if I plug in 2, we have 2 times 2 pi, so that's 4 pi. We plug in 0 for n, 2 pi times 0. So yes, we start at 0. So remember, we're starting at 0, we plug in 1, and then plug in 2 in this case. If there was 8, we plug 0 through 7. Now, something to note is when you start getting these large methods, this is the same both parts here, right? On your calculator, there's some things you can do to speed up. If you're using the same number, you don't have to input everything or the whole thing every time. So let's see, I want to make sure I'm in, I want radian mode. So, now the first one is, let's see, we had 1.03 plus, let's just say 2 pi, and then divide by 3. Now, that number we're going to use twice, so one quick thing you can do, hit store x, or theta in this case, and now all I have to do is say 34 raised to the 1/6 times cosine theta, and then do it again, go to entry, and change it to sine here. It doesn't save a lot of time, but using this entries button, entries, are you familiar with what that does? Pulls up what you previously entered in, and therefore you can change it and make any modifications. So doing these roots is probably one of the hardest things with chapters. Keep track of where all the numbers go, keep track of how we're going cycling through this. So any questions on what we're doing?